Hello, my name is Nadina, and in this video I'm going to give you an overview of the WHISKiT Physics Simulator. The WHISKiT Physics Simulator is a tool that was developed in the Hartman Lab at Northwestern University, and it is a 3D dynamical model of the rat whisker array. And I'm just going to assume that you're familiar with the rat with bristle system, but if you're not as familiar or you need a refresher, you have here in the GitHub repository, you have a link where you can get to the manuscript or the paper that was published in PNAS. This includes information about the rat with bristle system that is needed to use the tool with all the nomenclature and so on. And it also includes all the information about the development and validation of the model. So if you're interested in that information, you can check this out. But now in this video, I'm just going to give you an overview of the code itself and how you can install it so you can use the tool yourself. So also on the GitHub repo, you have here a video of the simulation output, so you get an idea what this tool can do. Here you have a 3D visualization of the simulation themselves. You see a rat head with all the whiskers that are simulated, and here they move back and forth in a whisking motion and collide with two pegs. Here on the left, you have the right side visualized. So each of these circles represent a whisker follicle, and the colors indicate a moment. Here in red and in blue, you have the forces for each of the follicles. Also here you have a vector visualization of those same dynamics. Here at the bottom, you have it ruled out in time. So on the y-axis, you have the whisker identities, and on the x-axis, you have time. The colors indicate the magnitude of the moment, and you can see how you see this whisking motion at 8 Hertz emerge in this graph. The tool can also give you information about where the whisker collides with an object. So here, from white to black, it shows you where along the whisker collides with an object. So you have this all collision information also again on y-axis, the whisker identity, and then you have it over time where the whisker makes contact with these pegs. Just this is to give you an idea what the tool can do, but you have a lot of ways how you can change these simulations to adapt it to your own scenario, and we're going to talk about that later in this video or in another video. So if you'd like to install this tool, you need to know that currently it's only available for Linux environment. If you are able to figure out how to compile it on a Windows distribution, I would love to receive a pull request from you so we can incorporate that in the repository. But for now, it's only working on a Linux distribution, so you can do that easily by just installing a virtual machine on your computer. With Windows 11, it's actually very easy to do. So you just go to the Microsoft Store and you download and install the Ubuntu essentially partition. You just allocate a little bit of storage of your computer, and you will be able to run the simulations. The simulation output is not very large. It's all text files, so the footprint is pretty small, but if you're obviously running tons of simulation, you have to be aware of how much storage you might need. So once you've installed your Linux, you will have to install some dependencies, which is one is FreeGLUT3, which is for the graphics, and you need Boost. Here it says 1.62, but actually it works with a later Boost version as well. So then you go ahead and you clone the repository. I assume you're familiar how to clone a GitHub repository. And now I'm going to walk you through how to install the tool. I'm personally I use VS Code. It's my preferred editor, especially because now you can easily just open a terminal with starting up Ubuntu, and that actually works really fine. I tested this, and this is very convenient to do it like that. You don't have to start up a virtual machine separately and then go in there and so on. And it will also keep all the installations you do on this virtual machine. So this is very convenient. So when after you clone the repository, you'll have two folders. You have a code folder where all the code lives, and you have docs. Docs just has some images, so don't worry about it. If you open the code folder, you have bullet.lib, which is the bullet physics library, which is basically the meat of the simulations. This is all this handles the physics, and but you don't have to worry about this at all. You just let it be there in the background and let it do its thing. So you have some other folders I'm going to talk about later, but first let's try to install this. So the first thing you do is to create a build folder with the command mkdir build. So you have a build folder, you go into that build folder, and the next command is cmake ... which will call the cmake list file, which includes all the compiler instructions and which will also check for all the dependencies. So if you have something missing, this will give you an error. So I'm going to do cmake ... and press enter. So I'm just waiting until this is completed. You will have some warnings, but that's totally fine if you do, as long as it's going through. And you see here now actually that I have installed Boost 1.71, which is working fine. Good, so it's done. It has written all the build files into the build folder. Now you just do make, and do the command make. Now this will take a while, so I'm going to skip that in the video. It probably is going to take you about 10-15 minutes until this is completed. So I'm just going to make and enter, and then you'll just wait until it has installed everything. Especially it will take a while because it will have to compile also the bullet physics library too. So you're just going to wait, and I'll see you in a little bit. Okay, and so this is now installed. You see 100% build target, blah blah blah. This is all bullet library stuff, so don't worry about it. So now we have it installed. Just going to clear my terminal. And now you can see in your build folder, you will have two executables. So one is WHISKiT, and that's the simulations without any graphics. So it will run a bit faster. If you need to do a lot of simulations, I would recommend you using this. If you need to double check your simulations and you want a visualization of it, you can use the WHISKiT GUI. So, but you don't have to specifically worry about these two files too much, because you can go to the scripts folder and you will have examples of bash files how to run the simulations. So these 5 scripts basically are 5 different examples what you can run with this model. So if let's take the run peg active, which is the one that you saw in the video earlier in the GitHub repository. So this will, in the first line, you have what it will, like the executable it will call. So for example, you can modify this to just WHISKiT if you want to run it without the graphics, or you can leave it with GUI if you want to see the graphics. Then you have different parameters here. So obviously that might not make much sense to you here. If you want to know what these different parameters mean, I'm not going to go through them all. So you can go to the source folder and you go to the parameters file. Here you will have all the default values of these parameters and a short description of what it is. So if you need to find a new parameter or you need to look up what it means, just go here. Just briefly, there are some simulation related parameters, as you can see, for the simulator. So you will choose a time step. Do not change that time step. It will not work with your simulations. Just leave it as it is. And what you can change is the time, how much you want to simulate, but that's also related to how much you give in the pre-computed whisking trajectory, which I'm going to show you in a second. Importantly, you have different ways of printing out stuff. So currently it's print 2, which will show you how much you've simulated in terms of time and how much is left. And importantly, you have a save button where you can save the output or not, and you can save a video or not, but the video actually will need an additional package, which is the FFmpeg package, which you need to install. So going back here, what you see with cdist, cpitch, cyaw, this is all camera related parameters. So if you go back to the parameter file, scroll down, you have here camera parameters, which is really just for the visualization, how close you are and where you position the camera and how it is angled. So if you want a different view, you can play around with these parameters here. Then you have a few example objects you can choose from. You can find those as well. If you go to the simulations file, you can see more about that, but that maybe in another video. So as I mentioned, you have a time stop, but you will need to pre-compute the whisking trajectory, and that will determine your time, but you can always choose a shorter time. For example, here I have pre-computed a second for the simulations, but I can't just simulate a quarter of a second to make it run faster or like shorter. You can active means you have actually a whisking trajectory, so they're moving. If it's 0, they will just be stationary. Most importantly, you have here whisker names. So R means you just simulate the right side of the array. You can also do the left side, or you can do all whiskers, or you can choose just specific whisker identities here, right? But so for now, we just do the right side. As I mentioned, you can save a video of your simulations if you want to, but you need additional packages. And you probably want to save the output here. So I'm going to show you how to run this now. So that's also fairly simple. So then you have to make sure you're saving your bash script to run it. One last thing, model type, you have the option to choose between the model that is basically the average array based on data that was collected by the lab, or you can use the model which will calculate the whisker geometry and morphology based on equations, and you can choose between the two if you'd like. So yeah, let's just run this together now. So I'm going to go out of this folder build and I'm going to the scripts folder, and to run it, at least in VS Code here in the Ubuntu distribution, to run it I do simply bash and then I select the script that I want to run, and that should now run the simulations with the visualization. So let's see if that works. And here a window opens and you see here you have the right side of the array. It includes all the whiskers of this side, and you have a peg positioned, and the whiskers will move and collide with this peg. So it just, and now you see the output, which you can change and go into the code to see what you'd like to select, or even change your code so you can print out different things. But here you see simulation time. I've simulated 0.1 seconds now, and I've completed 40% of the simulation, and I will be simulating for another 30 seconds. So obviously it takes much longer the simulations take much longer than they would be in real time. So this is now essentially a whisk at 8 Hertz. So I'm going to simulate 2 whisks for this simulation within a quarter of a second. Yeah, now we're done soon. Another 10 seconds, and then this should be completed. So now it's saving the data. It will save the dynamics, the kinematics, and the whisker identities. So then you find your simulation output in the output folder. So it will create a folder for which you specify the path. I recommend to use the output folder for your simulation outputs, but obviously you can change that. The reason I recommend that is because there are other example files that use this folder as input, but obviously you can adjust all that as you want. So see, here you have like full array peg active folder. So now I have the simulation output here. It will have 2 folders, like a dynamics folder and a kinematics folder. In the dynamics folder you have a file for each component of the mechanics, so fx, fy, fz, mx, my, mz, and each contains the forces or moment for each whisker over time. For the kinematics, when you open that, you have 4 folders, C, X, Y, and Z. C is for collisions. So when you open that, you have a file for each whisker, and in each of these files, you will have the collision binary response for each element in the whisker. So each whisker is composed of 20 links. So along the whisker, you have 20 elements, and each will have basically a time vector that is 0 or 1, whether it's in collision or not. And the same here, you have X, Y, and Z, each of which contains a file for each whisker where the X coordinates of each element is recorded over time. Same for Y and Z. And it will also output the whisker ID. So if you don't, it's basically just keeping a record of which whiskers you've simulated. So if you only simulate the RA0 whisker, you will only find that identity here in this file. That's just for reference. Then these 2 files, a MATLAB file and a Python file, you can generate with the scripts folder. I already did that, that's why they're already here. So if you go to scripts, plot signals, you have this Python file here, which you can use to also just see how to read the CSV files. I created here a few functions that make this easier, and you can install the PyResearch library that I created, or module that you can install, and then you have some functions here for plotting, for reading files, but also to especially for WHISKiT specifically, you can use functions that make all this easier. And yeah, so you actually see here is the link to that module, and you just follow the instructions of the repo to use this. So this basically just saves a MATLAB and a Python file, but it also plots a few things just for get an idea how to do this. So I'm not going through this, but that's where you can find it and use it as a reference if you like. And it will generate this MATLAB file and this Python file, and where you can process the signals further. Just makes it easier. So yeah, so this is basically how you can run a simulation based on these bash scripts here. Obviously, there are ways how you can change the simulations, and I'm going to talk about that in another video. Thanks for watching. Bye.